Grade 11s, and welcome back to my channel. I'm going to be starting with the first topic in grade 11, which is vectors. In today's video, we're going to be looking at the resultant vector and different vector directions. So how to state the direction of your vector correctly when giving a vector as an answer. Now, this video will be in 3 parts more or less. There'll be an explanation, very brief, only the things that you need to know. Then we'll be practicing examples, and right at the end I give you teacher tips. These are special tips, and it's because I've been working as a teacher setting papers, marking papers for years now, so you want to stay tuned for that. Let's jump right in. Behind me is a list of more or less the topics that we will be covering in this playlist together. It won't necessarily be in the order that I put it behind me over here, but we will be covering all of these subtopics. So if you're looking for videos on these topics, they're either already in the playlist or I'm in the process of making them and adding them to the playlist. So stay tuned. Remember to subscribe for more videos. But in this one, let's focus on what the resultant vector means. What does it mean? What is it? And how do we determine the different vector directions? Now, you should remember this from grade 10. A vector is a physical quantity with both magnitude and direction. What makes vectors special is the fact that you need to include a direction with your vectors. Mark all the way up to matric, we do not give answer marks for vectors unless they have direction. Now, what is a resultant vector? So you may or may not have gotten this definition given to you in grade 10, but it is a grade 11 definition. And grade 11s, what that means is you need to study this word for word. We can ask you this definition in an exam, and you should know by now that definitions are quite important. You need to be able to quote them, you need to be able to state them. So what is a resultant vector? A resultant vector is a vector sum of 2 or more vectors added together. It's very important that you mention vector sum. Sum means addition. So we take a lot of different vectors, we add them together, essentially, and that gives us a resultant vector. Or an alternative definition for resultant vector is a resultant vector is a single vector, so one vector that has the same effect as 2 or more separate vectors together. So let me show you an example of what that means. Let's pretend that I give you this and I tell you that that is our resultant vector. Let's call it R. Now that vector, basically, what that vector is composed of are 2 separate vectors. One that's pointing to the right and one that's pointing up. And you could be like, ma'am, how did you know that? How does that make sense? Look at this vector. Look at R. R is going to the right and it's going up. Can you see that? It's going to the right and up. Okay? So if I break that down, we get a vector going to the right and a vector going up. Let's call this R to the right and let's call this R up. I will teach you proper words for this later, but the point of this is if you take these 2 vectors, these 2 red ones, and we combine the effects, we end up with this black one over here. Okay, another way to think of it is, say you decide to take a walk and you start your walk over here. Then you walk this way and you stop here, and then you walk up like this and you end here. You started here, you ended here. Yes, you did there, you went there, and then you went there. But overall, from start to finish, what did you do? How did you get from your start position to your end position? You could have gone from here to your end position. So I hope that makes sense, that those 2 vectors that are going like that, together they give me the resultant vector. That's all that a resultant vector is. But you need to know how to calculate a resultant vector. Before we get into how to calculate a resultant vector, it's very important for you to understand how to quote or how to state the direction of a vector. There's different methods for stating the direction of a vector. Okay, now you might be thinking, ma'am, what are you talking about? If you go back to your previous video, if my vector looks like this, isn't the direction to the right? So say, for example, this is 10 Newton. Isn't it just 10 Newton to the right? Yes, it is. Or 10 Newtons east, or 10 Newtons in the positive direction. All of those answers are correct. What if I had to give you a vector like this? 10 Newton. That would be 10 Newton up, or 10 Newton north, or 10 Newton in the positive direction. So when vectors are acting in one dimension like this, so either straight up or down along the y-axis, or straight left or right along the x-axis, stating their direction is easy. But what's not easy is if we have a vector like this, like that first one I drew you, and it acts at a specific angle, okay? If you have to draw that in a Cartesian plane, it'll look something like this. Right, so in this example over here, so this was the first one we did. 10 Newton to the right would be this example. This would be 10 Newton up. Those are easy peasy. But what if my vector looks like this one over here that I've drawn on my Cartesian plane? Do you see that it's not going straight up or straight down? It's not going to the left or to the right. It's not doing that. It's acting at an angle. So how do you give that direction? You can't just say, I know, ma'am, that this is north up here, and this is east, and this is south, and this is west. So that vector must be 10 Newton north of east, or 10 Newton east of north. It's not enough information. There are other ways that you need to be able to tell me the exact direction of this 10 Newton vector over here. When I say this 10 Newton vector, I mean this one over here. You need to give me the exact direction, and you need to mention this angle as well. So how do we do this? What are the different methods? Let's have a look. So the three methods that you need to know in order to state vector directions are bearing. It's a very easy one. We don't often ask this one in the exams, but it's good to know. Those of you that do geography, you may know bearing. Number two is the Cartesian plane. That's supposed to say plane. Cartesian plane from the positive x-axis. And number three is the compass direction with the angle. So let's take a look at bearing first. What is bearing? Bearing relates to the compass. We all know the compasses look like this. Well, if you don't know, here's a reminder. Never eat sour worms. North, east, south, west. If you are north, you have a bearing of 0, east 90, south 180, and west 270. And guys, how I got those numbers, it's just that bearings are measured in a clockwise direction from north. So if you have to take your vector here, as you open it up this way, the angle gets bigger. So if I had to draw a vector over here, that would maybe be a bearing of 45 degrees, because you see that arrow is 45 degrees from the north line. If I had to do an angle or a vector like that, it would be at a bearing of 90 degrees, because it's not at the north line, okay? If it's at the north line, if it's straight up like this, it would have a bearing of 0 degrees. That vector over here, remember I'm talking about that last one that I just drew in here now, this one over here is lying on the 90-degree line. So it doesn't have a bearing of 0, doesn't have a bearing of 45, it has a bearing of 90. And then as you go to south, you get a bearing of 180, and so on. So vector A, what is the bearing? What is the direction of vector A? So you would say A is 10 newtons at a bearing of, what is the bearing? At a bearing of 50 degrees. If you said a bearing of 50 degrees, you are right, because they tell you here that this angle is 50 degrees. B, they tell you over here, they give you a measurement of 210. Now what I think is missing is an arrow that goes like this. So basically from the north line all the way around to vector B, this over here would be an angle of 210. So vector B would be 50 newtons at a bearing of 210 degrees. To give you that, and then they have to say that this is 30 degrees over here. Now remember, bearing goes from the north. So it's from where the north is, it's that angle over there. How do you get that angle over there? It's not 30 degrees, okay? What this sketch is telling you is that this little piece over here is 30. We want to know what this whole piece is over here. Well, think about it like this. This is how I like to think about it. From north to south, because remember south is down here. From north to south, what angle is that? 180, it's a straight line, 180. And then we need to include this little piece over here. What is that little piece? It's not 30. Remember, 30 degrees refers to that angle over there. So how would you get this piece over here? Well, north, east, south, west, but I'm sorry, that should say west. Between these two over here, this angle here is 90. Okay, so 30 plus what gives me 90? Yeah, 30 plus 60 gives me 90. So if this is 30 over here, this must be 60. And again, how did I know that? Because these two must add up to 90. So to get the bearing of this angle over here, or this vector over here rather. You start at the north, you go all the way over here, it's 180 plus 60, so that is 240, at a bearing of 240. I hope that helps. Let's jump into the second example of stating direction. The second type is a Cartesian plane. Okay, again, I've got the E, from the positive x-axis. Now, we all know in maths that the y-axis is this one over here, the x-axis is this one over here, the positive x-axis is this. Okay, I mean, if you had to label this, that would be 0, 1, 2, la, 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 and this way would be negative. So this is the positive x-axis. So how we do this direction is we look at the vector line. So say the vector line is over here, and we want to give the direction. Let's pretend I give you that as 30 degrees. You need to tell me the direction of that vector, let's call it vector A. And I would tell you that that direction is 30 degrees. Let's see if you can figure out why. Clockwise relative to the positive x-axis. So why am I saying 30 degrees? Why am I saying clockwise? So basically you start at the positive x-axis, okay, and you move downwards. Starting at the positive x-axis and I'm moving downwards until I hit the vector. That's 30 degrees. And did I go clockwise or did I go anti-clockwise? Now let me just show you. So this way is clockwise. That way is anti-clockwise. I know most of you guys use your cell phones to tell time now, like digital time, so you may not look or use analog clocks often, you know, the clocks with the hands, but that's where clockwise and anti-clockwise comes from. It's what the clock hand is doing. Okay, here's the positive x-axis. Do you see that that vector is going like this? Whoop. It's going down like this. It starts here, it's going down like that. So it went clockwise. I hope you can see it. This way, going that way is clockwise. This way. Okay, going the other way is anti-clockwise. So this is 30 degrees clockwise relative to the positive x-axis. Relative just means that's where we're starting. So let me give you another one and let's see if you can do it. Okay, so here's your next one. If you need a second to pause the screen and try it, do it. But I'm going to do it with you now as well. So remember the positive x-axis is over here. So the direction, you start at the positive x-axis. Okay, let's extend this vector. Let's make it a little bit longer. Like that. You start at the positive x-axis. Where is the vector? Okay, the vector's not down. It's going that way. So we're going to go this way. Are we going clockwise or are we going anti-clockwise? Remember, a clock's arm would go this way. We're not going that way. We're going in the opposite direction. So we're going anti-clockwise. So this vector, let's call it vector B. So vector B is 45 degrees anti-clockwise relative to the positive x-axis. There we go. Okay, I hope that helps. Let's see if you can do two more. V2 is a little bit more tricky. Okay, so V1 should be easy. So you start at the positive x-axis and we're going to go this way. So again, this is 30 degrees. Clockwise. Look at the direction that we're going. We're going this way like a clock. 30 degrees clockwise relative to the positive x-axis. Here's your answer for V1. What about V2? So here's V2. So you start at the positive x-axis. There's actually two answers for this one. I can either decide to go clockwise. If I go clockwise, I'm going to start here and I'm going to go all the way around and end over there. That would be going clockwise. But what is this big angle over here? Well, this would be 90. Okay? From this over here to here, that would be 90. Then that would be another 90. And then we go this little piece over here. So how much is this little piece over here? Well, if this is 20, this over here must be, remember, this one and this one must add up to 90. So if this is 20, this one over here must be 70. So in total, you go 90 plus 70, and that will be your bearing. So if you do clockwise, V2 will be 250 degrees clockwise relative to the positive x-axis. But what if you decided, ma'am, why would you go all the way around? Why would you go clockwise if you can just go like this? Anti-clockwise. You can do that. So what would that be? That would be 90, because this part over here is 90, plus 20. So that would be 110 degrees, but then you won't say clockwise. You will say anti-clockwise relative to the positive x-axis. There we go. 2 answers, 2 options. In our third method, we're going to be looking at the compass directions with an angle. So how do we do this? In this example, I want to give the direction for vector A. Okay, vector A is this dotted line over here. I'm given an angle of 50 degrees over here. So what I could say is vector A is 10 newtons. 10 newtons is the magnitude, that's not the direction. The direction cannot be north of east. And remember, I know you guys are saying, but ma'am, it's between north and east, so why can't it be north of east? We're going to be using north and east in our answer, but it has to be specific and we have to include a degree, a angle, so 50 degrees. So we'll say vector A is 10 newtons, 50 degrees, and look at what the vector is doing. Okay, this vector is going towards the east of north. So you would say east of north. And this often confuses students because they say, okay, ma'am, you said east of north, 50 degrees east of north. Can I say 50 degrees north of east? And the answer to that is no, because the order of the words, it basically is determined by which way the vector is opening. That's how I like to think of it. So I like to think of this vector line as going this way. It's opening up that way. It's going to the east of north. So another way to think of it, I also tell my students this, is whichever compass point it's closest to. So you see the 50 degrees is wedged between the vector line and the north line. That goes last. So north goes last. So if I had to give you this angle here instead, say I didn't give you 50 degrees. Say I gave you this one over here. Say I said 40 degrees over here. And I said, what is the direction of vector A? You would say, okay, A is 10 Newton, still 10 Newton, but now I'm giving you the 40 degrees, and it's 40 degrees, but now your answer is north of east. Do you see that they swap? North of east. Now you might still be confused. Ma'am, why are the words swapping? Think about it. The vector is, the 40 degrees is here, so it's like the vector's opening this way. It's going to the north. Do you see how it's lifting up? It's going to the north of east. Again, the shortcut way to think of it is the 40 degrees over here is wedged, it's squashed up between the vector and the east bearing or compass point. So whatever it's closest to, that goes last in the name. Okay, so here's one for you to try. Look at vector 1. Vector 1, if you look at the diagram, vector 1 is not lying on the east, right? It's not like this. It's going to the north. You see, it's opened up. This would be on the east. It's not on east. It's opening up towards the north. So it's 30 degrees north of east. There we go. What about vector 2? Look at vector 2. Vector 2 is not along the south. If it was along the south, it would look like this, but it's not. It's going that way a little bit. Okay? It's going that way a little bit. So it's going 30 degrees. Okay? East. It's going 30 degrees to the east of south. I hope that helps. It's very difficult to explain, but east of south. Okay, so it's going to the east. It's going that way of south. It's closest to south, so south goes last. Right, let's go into those teacher tips that I was telling you about. First things first. If you do not give a direction for your vector in your exam, you will not get the answer mark in the exam. Vectors need a direction. However, if they say give the magnitude of the net force, or give the magnitude of the velocity, or give the magnitude of the acceleration, magnitude just means amount. So a magnitude of a force would be 10 Newton, or 100 Newton, or 1,000,000 Newton. Magnitude just means amount, then you don't need to give direction. So if you see magnitude, you don't need to give a direction. It's amazing. Second teacher tip, very, very, very important. We in an exam, or whoever sets your exam, may force you to state direction using one of these methods. So you can't just choose all the time. Sometimes you can choose. Most memos don't accept bearing though, just check with your teacher. But for example, a question like this one over here can say, determine the resultant force and state the direction relative to the positive x-axis. If that's the case, you can't use the north of east or east of north. That's when you have to use the other method, the clockwise relative to the positive x-axis or anti-clockwise. Okay. In the next video, we're going to quickly go over an activity, this one over here, so I'll see you then.